Hello, this is Dr. Gardner. We're going to be talking about intermolecular forces today and how they affect different physical properties of substances such as boiling points and melting points. We'll see how it relates to things like surface tension as well as other types of strengths of interactions when we are predicting phase changes as well as vapor pressures and those types of physical properties. So first of all, if we look at intermolecular forces, they're quite important for helping us predict where their different substances might be in a certain state of matter at a certain temperature. So for example, if we ask ourselves, why is carbon dioxide gas at room temperature while H2O is liquid at room temperature? Well, if we look at what's going on with the intermolecular forces, that would help explain why they are in these different states of matter. One of the skills that's most important when we're making these predictions is being able to draw a correct Lewis structure, looking at the three-dimensional shape of the molecule and being able to predict how that relates to how polar that molecule might be. So if I can decide that one liquid might be quite a bit more polar than another, that might help us predict that the more polar liquid has a higher boiling point, because the attraction between the higher polar molecules will end up having a stronger attraction for the higher boiling point to occur, so they have to overcome that attraction for them to go to the gas phase. So that's kind of what we're predicting there. Now, if we really want to understand what's causing these molecules to attract with these intermolecular forces, well, that's exactly what we're going to learn to predict. We're going to go ahead and try to categorize the type of intermolecular forces that we have present, as well as the strongest intermolecular force present in predicting these different physical properties. So first of all, let's define some of our different types of intermolecular forces. We can first of all have London dispersion forces. London dispersion forces are the weakest type of intermolecular interaction, and they're present in all forms of matter. But sometimes there can be stronger interactions on top of this. So sometimes we can have a polar molecule, which, while a polar molecule has dispersion interactions, it also has a permanent dipole in the molecule, which causes intermolecular attractions. Now, if you get a very polar molecule that includes hydrogen directly bonded to fluorine, oxygen, or nitrogen, in those situations, we would say those molecules are capable of hydrogen bonding. So as we go down this list, our strength of interaction increases from dispersion forces to dipole-dipole interactions to hydrogen bonding. But in all cases, it's just electrostatic attractions between the charges present in our species and how strong those attractions are. Now, first of all, let's look at the weakest interactions with dispersion forces and work our way up to stronger interactions, such as with dipole-dipole and hydrogen bonding. Now, my London dispersion forces, as I said before, are present in all forms of matter. So when I'm looking at London dispersion forces, I really just need to consider the electron clouds that I have around the atoms in my different samples. So let's say that we're looking at a atom of a noble gas. Let's say it could be helium. So I have these two helium gas atoms. Now, with respect to those two helium gas atoms, there's very weak interactions between them, but you can get liquid helium. What would cause us to go from the gas phase to the liquid state is this weak attraction, these dispersion forces that can occur. So let's think about what's going on when you have London dispersion forces. Well, the electron clouds present in these atoms, or even in nonpolar molecules, when we have these electron clouds, they may appear at first equally distributed, but we can have temporary dispersions between them. We can get temporary distortions of these electron clouds. So in a sense, you can think about these electron clouds sloshing a little bit. So if you were walking through your kitchen with a pan of water, well, you know that it's very hard for the water to stay level as you're walking. Sometimes you end up with the sloshing of the water in the pan, causing a little bit more water to be on one side versus the other, just temporarily, even if you're trying to hold the pan very steady and level. Well, that's a little bit like what's happening here with the electron clouds. We can get a distortion between the electron clouds, and what can happen is if we have one electron cloud distort slightly, so there's more electron density on one side. So if I have more of my electron probability of finding electrons over towards the right-hand side of this first atom of this noble gas, well, since those electrons are being attracted to the protons on the next atom over, what we can have is that distortion of the electron cloud can be felt by the adjacent atom. So its electron cloud will distort, and we'll end up with repulsions. So we get this, what we call a temporary dipole. So I'm going to show a delta positive and a delta negative, indicating there's more electron charge or more electron density over on the right hand side, but it's a very temporary difference in the electronegativity, in the electron density of the cloud in this case, and the next atom over will feel that temporary distortion, and it will distort as well. So we get this very brief electrostatic interaction that's somewhat weak. Now that weak electrostatic interaction from the distortion of these electron clouds will cause a distortion that's a temporary dipole. So I might call these temporary dipoles. I might call them occurring from London dispersion forces. They're present in all substances. They're quite weak, but they would allow us in nonpolar species, such as noble gases or nonpolar molecules, to actually have enough attraction in order, under certain conditions, to liquefy or solidify. In fact, what we'll find is that we can start to predict how likely these clouds are to distort. So if I look at an atom or molecule and I consider the property of polarizability, I can make predictions about how likely those clouds will distort. And so let's say that we are looking at the polarizability of chlorine versus bromine versus iodine. Now, if we're looking at each of these, let's consider what's different between their electron clouds. The larger the electron cloud I have is correlated with the increasing molecular mass here. So as I go from chlorine to bromine to iodine, as I look at the periodic table, I'm increasing from 35 for the atomic mass for chlorine, 35.45, to 79.9 for bromine, to about 126 for iodine. And as I'm going down, I can see then that I have increasing atomic masses. I have twice that for the diatomic molecules, but what that really is telling me as I go down the periodic table is I'm adding extra shells of electrons, and those extra shells of electrons are further and further from the nucleus. Now I am adding more protons to the nucleus as I go down the periodic table as well, but there's additional shells of electrons between the outer electron and the protons in the nucleus. So those outer electrons are being held a little more weakly. That allows their clouds to distort more readily. So I get these temporary London dispersion dipoles, these temporary London dispersion forces that can occur. So these temporary dipoles, or these London dispersion forces, can cause very weak attractions. But as my molar mass increases, I expect that a term called polarizability is increasing. So the more weakly the outer electrons are held with larger molecular mass molecules, the more polarizable the electron clouds are, and the stronger these London dispersion forces will be. So just correlate. Increasing molecular mass for nonpolar species or atoms will have increasing London dispersion forces, increasing temporary dipoles that are being formed in strength. Okay. Now, let's try to make a few predictions. So if I look at helium versus krypton, well, if you look at your periodic table, we can see if we look at helium, well, helium has a mass of about 4 atomic mass units. If we look at krypton, well, krypton is going to have a mass of about 84 atomic mass units. So what I'm seeing is as I have the increasing atomic masses here, so AMUs, or I could relate it to molar masses, right? Grams per mole. But as I have this increasing mass, what we're adding is extra shells of electrons, and those extra shells of electrons are further and further from the nucleus, with more shielding occurring from the inner electrons, and so I expect that that polarizability is increasing. So I can say polarizability is increasing as the molar mass increases. So I expect that I have that increasing polarizability, higher molar mass. I'm going to end up with having higher strength London dispersion forces. So krypton would have a stronger London dispersion forces. It would be expected to have higher boiling points and higher melting points. Okay, now let's consider hydrogen chloride versus hydrogen bromide. Now, if I had these in water, I would call this hydrochloric acid and hydrobromic acid, but in the gas phase, I could call it hydrogen chloride gas, and I could have hydrogen bromide a gas potentially. So if I'm looking at these two gases and I want to consider which has the stronger London dispersion forces, well, I could go ahead and look at the increasing molar mass. So as I go from chlorine to bromine, my chlorine's mass is 35.45, my bromine's mass is 79.90. I have just a hydrogen on each of those those, but that doesn't change the mass. So as I have increasing molar mass, I have increasing polarizability, so the London dispersion forces have also increased. As we'll see later, though, we also have to consider how polar these molecules are, but we haven't gotten to talking about permanent dipoles quite yet. So I have increasing polarizability here, so that's going to cause the London dispersion forces to be stronger. Now, if we look at methane versus ethane here, again, I just have carbon and hydrogens here, but if I look at my molar mass for my methane, I have 2 fewer hydrogens and 1 fewer carbon, so the molar mass is less here for methane and increases to ethane. So I expect that as I have that increasing molar mass, that I would have a higher strength London dispersion types of forces. I'm also getting greater surface area for the interactions for these dispersion forces as I get larger molecules, so that's increasing the polarizability as well. So those are some things that I'll tend to look at. So we decided krypton was the stronger London dispersion forces because of the higher molar mass here, hydrogen bromide, and your ethane. Okay, so let's consider these two molecules. So I have methane and silicon tetrahydride. If I look at these two molecules and I want to decide which has my stronger London dispersion forces, well, the hydrogen masses are identical. There's 4 hydrogens in each. So if I look at the mass for carbon, so my mass for carbon is 12.01 atomic mass units, AMUs. My mass for silicon, if I look at silicon, is going to be 28.09. So about 28 atomic mass units. And the shapes of these molecules are identical. If I draw the Lewis structures out, I have a tetrahedral shape for the methane as well as a tetrahedral shape for the silicon tetrahydride. They're both nonpolar molecules, so I'm really quite interested in these London dispersion forces because they're nonpolar. If I look at these, since I have an increasing molar mass from CH4 to silicon tetrahydride, I expect that my London dispersion forces increase. With that increasing molar mass, we say polarizability of the outer electron clouds is increased. For example, as I go from carbon to silicon on the periodic table, I go from period 2 down to period 3. In period 3, we're going to have an extra shell of electrons. Those outer electrons will be held more weakly, and we notice that the electron cloud will distort more readily, so the dispersion forces will be stronger in that case. So I can make some general predictions there. Now, let's go ahead and have a little class question here. Let's go ahead and predict if I look at neopentane versus N-pentane. And notice in these cases I have the same number of carbons and the same number of hydrogens between neopentane and N-pentane. I'd like you to think, would there be a difference in their intermolecular forces with their London dispersion forces? Would one have a higher boiling point than the other? And if so, which one would it be? So I want you to think about this as a class for a minute. Would neopentane have the higher boiling point, or would N-pentane have the higher boiling point, or would they have a fairly equal boiling point? I want you to think about that. So pause the video if you need to for a minute as you discuss this as a class. Okay, now that you've had a chance to discuss this as a class, I want you to go ahead and come up with what you've decided you think is the correct answer. Now, since these have the exact same molar mass, they both have a total of 5 carbons. They both have, in this case, 12 hydrogens. So we have the exact same number of hydrogens, exact same number of carbons, and these molar mass is identical. So I can't just use my molar mass relationships to predict which has greater dispersion forces. I have to think about what's going on with the shapes of these. So if I look at the neopentane, this nice symmetrical shape around that central carbon gives you less surface area, kind of like a little bit of a spherical shape to the electron cloud slightly. It is distorted a little bit from that. But you have much less surface area here, whereas if you have a long chain of carbons like in the N-pentane, well, that's going to have a larger surface area as you get this more type of long cylindrical shape. And as you're looking at that with that increased surface area, we can expect that there's more sites for possible interactions with a greater surface area. So you're going to expect that the dispersion forces are stronger. So now we're seeing that as molar mass increases, we usually can expect the polarizability of the outer electrons. The ability of the outer electrons to distort more readily increases and dispersion forces increases. But when you look at a case where you have very similar molecular masses, you can't rely on that. In those cases, you're going to be looking at which species has the greater surface area. It can often give you a prediction about the strength of the dispersion forces. So how many sites are there for them to interact with one another? One way to think about this, if you're looking at these two species, in fact, if I look at the boiling points for N-pentane versus neopentane. The boiling point for the N-pentane is 36 degrees Celsius. Still a very low temperature, but just a little above room temperature. But if I look at neopentane, it's 9.5 degrees Celsius, so it would be a gas at room temperature. So kind of important to look at that. What I can think about is when I have more surface area, if I get longer chains, one thing you can think about is they could get intertangled with one another. So imagine if you have a container full of marbles and you're pouring the marbles out. The marbles tend to slide past one another. They have the least surface area. But if I had a bowl full of spaghetti noodles, these long molecules, and I start to try to pour those, or if I start to try to look at their interactions with one another, there's more surface area for those to interact. And so they kind of get intertangled as well with one another with these longer chains with that greater surface area. So just kind of remember, greater surface area relates to more sites for the dispersion forces to interact at and increases the strength of the London dispersion forces overall to give you higher boiling points, higher melting points, a stronger intermolecular interaction in that case. Okay, now, why do we really care to study boiling points or melting points? Why should I study melting points at all? Well, if I continue on to take an organic chemistry class, what I might realize is that as I'm studying substances, we'll often go ahead and synthesize, meaning that we'll produce a new molecule in a chemical reaction process, and we'll study that molecule and try to identify what it is. One of the techniques to identify what it is to determine a melting point. And if that melting point matches the literature references for the melting point for that pure substance, that's a good indication that I have produced my target molecule. So what I can realize, though, is I need to go ahead and isolate very pure substances in the laboratory in order to measure these melting points. With a very pure substance, the melting point will be over a very normal range, usually less than 1 degree Celsius. So for example, I might record a melting point of a pure substance as being between 125 to 125.5 degrees Celsius. Now, if I get impurities in my substance, this melting point tends to be wider. In some cases, we might see the melting point spread out over at least several degrees, if not more. So that'll help me tell purities of substance. Very pure substances have a narrow melting point range. Impure substances have much wider melting point ranges. Now, the melting points, as I said, we're using them for three major reasons. First of all, as I said before, we can identify an unknown sample to see if it matches a literature reference for a melting point. We can also record new melting points for compounds that we're the first to synthesize and publish those for other individuals to be able to repeat our work so that, if they've synthesized the same compound, if they have the same melting point that they observe in their laboratory. Now, the third thing that we'll look at is we'll determine the purity of a compound. When we determine the purity of a compound, we'll go ahead and consider, when we're looking at solids, we'll decide if it's pure based on whether or not we get a broad melting point versus a narrow melting point. Okay, so a solid you might consider as very pure if you were to recrystallize it. By recrystallizing it, we will heat up the solid in a solvent until we form a saturated solution as we dissolve it. And then as we form that saturated solution at a higher temperature, we'll cool it down until we get a supersaturated solution, where we have more solute of that solid than is stable at that temperature. And then as it becomes supersaturated, as it cools, we'll very slowly grow crystals. In fact, we want to cool it very slowly so the crystals have very gradual growth. The slower the crystal growth occurs, the least likely they'll have, or the less likely they will have, impurities included in the crystalline lattice. In that case, you'll get a pure substance, and when you check the melting point, you'll see that the melting point would be higher, and you would see after crystallization that you'd have a very narrow melting point, which would indicate a pure compound. So you kind of look for those types of things with respect to melting points, but they're all related to how high those are for the melting points, be related to how strong the intermolecular forces are. If I only have dispersion forces, I usually have some of the lowest melting points. If I have stronger intermolecular actions on top of any dispersion of forces occurring, then we would have to consider those type of intermolecular interactions may be determining higher melting points. Okay, now when we determine the factors that will tell us the type of melting points that I have, well, when I look at molecular compounds, I'm overcoming intermolecular forces. The weakest intermolecular force is my London dispersion forces, those temporary dipoles we talked about from the distortion of the electron clouds. So I'll often try to make predictions with molecular masses, polarizability, surface area to determine if I have a non-polar compound with only dispersion forces present as to what their melting points would be. Now, if I get polar molecules, not only do I have London dispersion forces occurring because I always have these electron clouds with distortions, but I also have a permanent dipole sometimes when there's a difference in the polarity of the atoms, or the electronegativity of the atoms, I should say, on different portions of the molecule. In those permanently polar molecules, you get what are called permanent dipoles. So you get molecular dipole of one polar molecule interacting with a permanent molecular dipole of the second molecule over. Those dipole-dipole interactions happen to be much stronger than only London dispersion forces in most cases, though they both contribute. And so those dipole-dipole attractions will tend to give you higher melting points. Now, a really, really strong dipole interaction can be classified as hydrogen bonding. It's just a special classification of dipoles. And hydrogen bonding molecules will have a very strong dipole with a very large difference in electronegativity between the atoms, and some fairly small atoms that are bonded together to enhance this difference in the electron cloud permanently, with how the electrons are oriented around the more electronegative atom and not so much around the least electronegative atom. So hydrogen bonding tends to form when you are following what we call the H-bond rule. So if I have hydrogen directly bonded to fluorine, oxygen, or nitrogen, I expect to be following this H-bond rule. Okay, so this is the strength of my intermolecular forces going up. London dispersion forces are the weakest. They're always present. Dipole-dipole forces can be on top of London dispersion forces, and they can increase the strength of interactions. Now, hydrogen bonding is just a type of dipole-dipole interaction. I can still have London dispersion forces going on underneath it all, but the hydrogen bonding tends to give you the strongest interactions, like you have between water molecules. Now, even with these type of intermolecular interactions between molecules in covalently bonded compounds, they still mostly melt below 300 degrees Celsius when I overcome these interactions. Now, some types of substances have what we call network covalent bonds. Network covalent bonds would be where you have covalent bonds holding the bulk substance together, like when you have quartz or a diamond. In those cases, you actually have to break covalent bonds for the substance to melt. In those cases, you'd have much higher melting points. The melting points for my covalent compounds usually are actually overcoming just these intermolecular interactions between molecules without breaking covalent bonds. In that case, I expect melting points to be below 300 degrees Celsius. Now, ionic compounds, we don't have any individual molecules. All we have are cations and anions, maximizing their charge attractions and minimizing repulsions in their ionic lattices. With respect to those ionic compounds, we can expect that the melting points will be very high, because instead of having these partial charges that we might have with respect to permanent dipoles or just temporary dipoles with dispersion forces, in those cases, if I have a permanent charge in an ionic compound, I have much stronger attractions because I have complete electron transfer to form cations and electrons. Cations and anions as those electrons are transferred. So we end up with sodium chloride, for example, having a very high melting point of about 800 degrees Celsius. So ionic compounds have some of the highest melting points. Okay, so that's something to remember when you're trying to classify types of compounds. Now, let's go ahead and review what types of factors are determining higher melting points. If we're looking at nonpolar molecules, like as methane and ethane and propane and butane and pentane, these are all nonpolar molecules, so my strongest interactions are just dispersion forces, the distortion of those electron clouds. As you might expect, the molar mass is increasing as I go from methane to ethane to propane, as I get more carbon and hydrogens, and as I go from butane to pentane. So we're becoming less negative for my melting points. And so I can see that I have an increasing melting point, and I would also see an increasing boiling point predicted here as the molar mass increases from left to right as I go across. And that's because the London dispersion forces are increasing. Plus, I'm getting more surface area for interactions. So there's two factors involved there that relate to the molar mass in this case. The increasing surface area gives you more sites for intermolecular interactions with respect to the London dispersion forces. Okay, now, if we see these London dispersion forces becoming greater, we can see that we have higher and higher melting points and boiling points. So this is a graph that looks at boiling point versus my period on the periodic table, which relates to the increasing molecular masses. We also have greater polarizability as those outer electrons are held more weakly on the outside of the higher molar mass atoms. So as I go down a period, fluorine, chlorine, bromine, iodine on the halogens, we expect the boiling point is going to increase. We're seeing that also occur with respect to methane, silicon tetrahydride, germanium tetrahydride, and your tin 4 hydride here. As we're looking at those, we end up with having an increase in boiling point. With the dispersion forces, we're also starting to get a little bit more character that's acting a little more ionic in nature that would predict that we would have higher boiling points and melting points as well. If we look at the noble gases as we go down the period, we have an increasing molar mass and increasing polarizability as well. So that's trends that are easy to predict here. Now, the reason that we worry about looking at these intermolecular forces is they also relate to how we might purify different types of fuels in our society. So if we take something like crude oil, what we tend to do is remove fractions of crude oil through distillation towers. Your distillation towers will be heating up your crude oil, and you separate out fractions of the crude oil based on their boiling points. Okay, so natural gases are going to boil under 20 degrees Celsius, so I can separate those out as my highest fraction on the distillation column, and then I have lower molecular mass fractions or ranges of the crude oil and crude fuels that I can separate it out with respect to lower boiling points. As the boiling points increase, we end up with having lower fractions on our distillation towers, and we end up with having higher viscosity as well. So we're seeing viscosity also increase as we have stronger intermolecular interactions with dispersion forces with higher molar masses. So those are some things that I would look at. Now, if I consider moving from nonpolar molecules to polar molecules, so my polar molecules will have a permanent unequal electron cloud. We will have more of the electrons spending time by the electronegative atoms and less time being spent near the electropositive atoms with respect to the probability in the electron cloud. And so I look for polar molecules having a positive and negative end. Okay, a lot of times you're going to notice that when they have basically a lack of symmetry in many of those molecules. Now, so sulfur dioxide example is very polar. If we look at it, it's a bent shape. So we can see it's not symmetrical. We have sulfur here bonded to oxygens. Okay, and so if we look at sulfur bonded to those oxygens, well, we do have some resonance structures. I haven't drawn out all the lone pairs and all the resonance bonding, but if we look at that, the sulfur is going to be less electronegative than the oxygen, so I get a delta negative here by the oxygens and a delta positive by the sulfur. Okay, this causes a permanent dipole to occur. So we expect that in addition to any dispersion forces going on, because remember, if I have an electron cloud at all, there's going to be distortions of the electron cloud, but that's a weaker interactions. There's going to be a permanent dipole here. And so the permanent dipole in this first sulfur dioxide molecule will interact with the permanent dipole in the second sulfur dioxide molecule next to it. That attraction between these permanent dipoles causes what we call a dipole-dipole attraction. We're saying dipole-dipole because there's two dipoles between the two separate molecules causing an intermolecular attraction that's occurring, which tends to be stronger usually than the dispersion forces I would predict, even though they are all contributing to the attractions in this case. Now, if I look at a variety of molecules that have dipole-dipole forces, I might look at sulfur dioxide where I have an end that's a little bit negative by the oxygens, a little bit positive by the least electronegative atom, the sulfur in this case. So I'm going to put my Greek letter deltas for negative for a partial negative charge on the more electronegative atoms, a delta positive by the more electropositive atoms. Now, if I look at CH2Cl2, well, if I consider the electronegativity differences between hydrogen and chlorine, chlorine is much more electronegative than hydrogen if you remember your trends from the periodic table. Remember, our trends for electronegativity is increasing as we go up and to the right. So we expect that the chlorine here in green is going to be more electronegative, so that's going to be the delta negative end of my molecule here. And since this molecule is a tetrahedral shape, it's not symmetrical, we end up with a delta positive by the hydrogens. Now, sometimes students will incorrectly draw or think about this molecule. They might draw a Lewis structure that looks like this, and they'll sometimes forget that this is a tetrahedral molecule. So they'll see the two hydrogens written, and they'll see the two chlorines written, and if they think of this as flat, which it is not, they might think that's symmetrical and nonpolar, but they'd be wrong because it isn't lying flat. They aren't 90-degree bond angles. The bond angles here are going to be close to 109.5 because of the tetrahedral shape. So I actually have the chlorines could be coming out towards me and the hydrogens going into the plane of the slide here. Okay, so sometimes it's better to draw the similar atoms adjacent to one another when you draw a tetrahedral type molecule. So I might show the hydrogens on adjacent sides to kind of stress that there is this tetrahedral shape and remind myself that there's one edge of the tetrahedron with the hydrogens and the other edge with the chlorines. So if you draw it this way, it might help remind you that that's not as symmetrical as you might have been confused about with this structure. So that one has a permanent dipole that we can see. That permanent dipole will then produce dipole-dipole interactions. Now if I look at phosphorus trichloride, well, the phosphorus has a lone pair up here on the phosphorus, and so that causes a trigonal pyramidal shape. So it's very important you be able to draw these Lewis structures and predict the geometries as I draw them out. So if I see the Lewis structure here for phosphorus trichloride, we can see that lone pair on the phosphorus. It's causing all of the chlorines to be repelled and distorted down to form this trigonal pyramidal shape. So this trigonal pyramidal shape that we produce is going to go ahead and indicate that we have a polar molecule where we're going to have a lone pair of electrons that are going to be quite negative here, and the difference in the electrons being distributed will be different because of the chlorines lone pairs versus the phosphorus lone pairs. So we're going to end up with having a very polar molecule here as well that causes a permanent dipole. Now, however, if I look at boron trifluoride, now boron trifluoride is breaking the octet rule a lot of times as we write this, because what we'll see is that we end up with the 3 fluorines with all their lone pairs. In fact, let me draw it up here. So I have the boron with their 3 fluorines. We're filling the valence shell of the fluorines, and sometimes this will be written with some resonance forms as well, or you might consider it having an incomplete octet. As we're looking at this boron trifluoride, we can see it's nice and symmetrical in a plane. It's trigonal planar. In that case, we'd predict this as a nonpolar molecule with dispersion forces, but that it would not have a permanent dipole. So I would not predict boron trifluoride to have a permanent dipole. The other 3 we would say would have permanent dipoles with respect to this. So yes, 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 and no. Okay. Now let's say I give you the formulas of a variety of compounds, and we want to know which of these compounds have permanent dipole forces. Well, what you'd want to do in this case is you'd want to draw the Lewis structure for each of these and predict the whether you have a polar molecule or a nonpolar molecule. Now all of them will have London dispersion forces, but if it's a nonpolar molecule, the London dispersion forces will be the only intermolecular interaction and the strongest. Now if I do get a permanent dipole, I would expect those permanent dipoles would be stronger, and even though dispersion forces are underneath them, they would probably categorize into having the strongest type of interaction. So let's start with this. Let's look at sulfur trichloride. If I draw the Lewis structure, which is what I'll want to do to start with, for dichloride, we're going to end up with having 2 chlorines bonded to the sulfur dichloride, and we'll end up with 2 lone pairs on the sulfur, and we're going to end up with 3 lone pairs on each chlorine. So if I were to categorize the shape of this Lewis structure, I'd say that it's going to be bent in shape. And so that bent shape will go ahead and give me a permanent dipole. So in that case, I say there are dipole-dipole interactions. In this case, it's a polar molecule. Now, if I look at carbon dioxide, though, if I draw the Lewis structure, the best Lewis structure is going to have double bonded oxygens off the central carbon. So this is a linear molecule when we draw the Lewis structure. And we expect that this linear molecule will have no permanent dipole. So the stronger interactions here are just dispersion forces. So in this case, there's no dipole-dipole interaction, only London dispersion forces with this nonpolar molecule. We can also tell that there's some symmetry there with respect to a couple of axes, and so that indicates also that we will tend to have a nonpolar molecule. Now if I look at carbon monoxide, now carbon monoxide has a triple bond between the carbon and the oxygen, and I have lone pairs available. Now when I look at carbon monoxide, this is definitely polar. We end up with the oxygen being more electronegative than the carbon, so I get a negative end of the molecule and I get a positive end by the carbon. That produces a permanent dipole, and a lot of times you'll recall that we can draw a dipole as an arrow here, where we have the head of the arrow being the negative charge and the tail of the arrow being the positive charge. So we have this type of permanent dipole present. Okay. And that's going to cause dipole-dipole interactions with a polar molecule for carbon monoxide. Now, if I draw the Lewis structure for ammonia in the correct form, we can see that ammonia will have a central nitrogen. It has 3 hydrogens. And if you've drawn a correct Lewis structure for ammonia, you'll have extra electrons that aren't required on the hydrogen, since they only want to follow the duet rule. They only want 2 electrons on each hydrogen. So we put the extra electrons as a lone pair on the central nitrogen. So because of that, the lone pair of those electrons on the nitrogen will distort down the bond angles, and that causes a trigonal pyramidal geometry. And so I get a partial negative by the lone pair and partial positives out here by the hydrogen. So it's definitely permanent dipoles. And in fact, we're going to give this a special category. The strength of the dipole-dipole interactions here are so strong, they're following the H-Von rule, with hydrogen directly bonded to nitrogen. But remember, the H-Von rule says that if hydrogen's directly bonded to fluorine or oxygen or nitrogen, and in this case we have hydrogen bonded directly to nitrogen, we have hydrogen bonding, which is a really strong dipole that we give a special name to. So not only could we say we have dispersion forces, which are present in all molecules, and dipole-dipole interactions, here we can say we have a special dipole-dipole interaction called hydrogen bonding in this situation. Okay, now if we look at carbon tetrachloride has a nice symmetrical shape. So I have carbon in the center, I have my 4 chlorines. Each of the 4 chlorines have 3 lone pairs on them when I draw the Lewis structure out. So it's a tetrahedral shape because I have 4 bonding groups to the central atom. So that tetrahedral shape here is nice and symmetrical. So even though I have electronegative chlorines on each edge of the tetrahedron, the symmetrical nature of it will cancel out the dipoles. So I would say this is nonpolar. So really my strongest interactions here are just dispersion forces. Okay. Just as a reminder, if I were to write my A at C notation, the central atom carbon is A, and the ets atoms are the bonded groups. So I'm going to go ahead and have AX4 for my notation. Okay, or you could say there's E0, there's no lone pairs on the central atom. Okay, so go back and review your AX notations as well. Okay, so I want to finish here today talking about one more type of interactions. If I consider basically hydrogen chloride versus hydrogen bromide, in water I would name them as acids, hydrobromic acid and hydrochloric acid. But if I'm considering them in the gas phase, I could have like hydrogen chloride and I could have hydrogen bromide. If I want to consider which one of these is more polar, I have to think about the electronegativities. Now the electronegativity for chlorine is greater than that for bromine. So if I was going based on electronegativities alone, you might decide that the chlorine would have the higher melting points or boiling points. However, when I'm considering these, even though there's a stronger dipole interaction due to the hydrogen chloride versus hydrogen bromide, I also have to consider dispersion forces, because if I study this, I find the boiling point for hydrogen bromide is actually higher than that of hydrogen chloride. The reason for that is I have a much higher molecular mass, so even though I have a stronger dipole interaction with HCl, I also have stronger dispersion forces for the hydrogen bromide. So the dispersion forces of the hydrogen bromide with the more polarizable electron cloud with the bromine's higher molar mass explains the higher boiling point. So sometimes you'll find with higher molecular masses that your boiling points may be distorted to be higher due to having that greater polarizability. So you have to consider both factors. Okay, so that's where we're going to finish today. Next time we'll talk a little more about hydrogen bonding and how we can predict properties with all the intermolecular forces. Thank you very much, everybody.